We're now going to take a closer look at this special gradient function that we defined previously. And the gradient it's not just a convenient tool to denote a directional derivative. It in its own right, it is very, very important. And we're going to explore some of those important properties over the next couple of videos. So the first video, let's just again kind of recap, where we are, right? So we have this idea, this thing that we call the directional derivative, which again, in a nutshell, you can describe as the rate of change of this surface at this point in this direction. So maybe a kind of a big nutshell, but we can summarize it in one sentence, right? But there are those three components: surface, point, direction, and then you're trying to find the instantaneous rate of change in whatever direction now, as long as we have that direction defined as a unit vector. But then we saw that we can express this in this form, right? And we should be pretty familiar now with all this notation. Just a little reminder that the U1 and the U2 are the components, the respective components of our unit vector, right? So our direction vector, if you will. But then we saw that if you look closely, you can see that this is really just a dot product in disguise. It really is the dot product of these two vectors. So the f sub x of x0, y0, and then f sub y, x0, y0, and then the other vector would be your u1, your u2. So that's your direction vector that's been normalized. And then here is the thing that we now call the gradient. So let me write it this way. This is now so we'll use this notation. Now this upside down triangle, or I mean, who's to say what's right side up, upside down? But this symbol, it's often referred to as del, right? So we call it the del operator. And sometimes it's called nabla because of its similarity to in form to an ancient Hebrew 10-stringed harp of that name, right? So yeah, there's a little history lesson for you. So the gradient, this notation for the gradient as opposed to the grad, this we either read this as just del, right? Or nabla. So if you want to get really fancy, you can call it nabla, right? But yeah, so we're going to use this notation. And what this is, it's the gradient of our surface, and then it's evaluated at the point. So x0, y0, and then I'll just do dotted with our unit vector, right? So basically, what we have here are three, I mean, obviously these are all equivalent. The only thing I didn't write down was the definition, the formal definition of the directional derivative. But we have all these different ways of interpreting and denoting this one thing. And we're gonna look closely at this, the dot product version right now, right? Well, what do we know about dot products? Well, we know dot products have a geometric interpretation and also an algebraic interpretation. If we focus on the geometry of the dot product, right, we can actually gain some deeper insight as to, this whole gradient thing and what exactly does it mean, right? So I'm going to write something on one line here because I want everything to be clear. I want it to be super clear that all these are equivalent forms. So we have our notation. We now have this gradient form of the directional derivative. And since it's a dot product, let's think about what we know about the dot product. The dot product can be expressed in terms of angles and magnitudes, right? Or maybe specifically one angle and two magnitudes. The geometric way of computing the dot product is this. If I can find, now remember, both of these are vectors, right? We can see them right here. The gradient is a vector. And of course, our unit vector is a vector. So the alternative way of computing the dot product says, well, I could take the magnitude of my gradient vector, right, multiply the magnitude of my direction vector u, and then multiply that by the cosine of the angle between them. So I'll just remind you, so this is where theta is the angle between, and I'm running out of room, oh no, between the gradient and u, right? So there we go. So we have the, so like for instance, up here, we've already used like the dot product, the algebraic version of the dot product. That's this one right here. And now we're expressing it in this alternative form in terms of magnitudes and an angle. But we can go a bit further right here and say, well, because u is a unit vector, and that is by definition, the magnitude of the unit vector is 1. So that is equal to 1. So I can simplify the geometric formula even more. I can write it as the magnitude of the gradient, right, at that point, times the cosine of the angle between them, right? Now, when we say between them, again, remember, these are two vectors. And in a second, I'll sketch a couple things that might emphasize that. But these are two vectors, and the theta is the angle between them. So when I look at this, right, and so this is like an alternative formula for our directional derivative. It's simply the magnitude of the direction of the gradient vector times the cosine of the angle between them. So then it kind of leads itself to an important question, which again is an important question going all the way back to, when in your start of calculus, like how large can this directional derivative be? Like what is its maximum value? So in other words, like what is the maximum rate of change that the surface can observe at a specific point, right? Or what is its minimum rate of change, at a specific point, right? So let's think about it. The magnitude here, this is always positive, right? The magnitude of the gradient, the magnitude will never give you anything negative. So this is always positive. But we know the cosine function, it oscillates between plus or minus 1, right? So cosine of theta, it oscillates, right, between plus or minus 1. In other words, since this is always positive, and this is a fixed number, right? So at a fixed point, this is really just a constant positive number. So the only thing that really changes in this formula is the cosine part. Then we can ask ourselves, well, what would have to happen to the cosine, right? Or what would have to happen to this factor in order to get the maximum possible directional derivative, right? Well, if you think about it, if this is always positive and it's a positive constant, then the whole expression here is as large as possible when cosine is as large as possible. So if cosine is maximized, then the entire thing on the right-hand side, this product is maximized, which by just following the breadcrumbs, right, takes us back to our directional derivative. So this rate of change has a maximum value when cosine of theta is maximized. Well, what value of theta will maximize cosine? Well, let's think about it. Cosine, if it oscillates between plus or minus 1, then clearly positive 1 is its maximum, right? So cosine theta has a max value of 1 when, so then we have to ask ourselves what value of theta will produce that maximum value. Well, again, remember, since theta is the angle between two vectors, let's go back here. We're connecting lots of dots right now, so I'm super excited. I hope you are. So remember, theta, because it's the angle between two vectors, it's anywhere between 0 and pi, right? And again, we're using radians because we're deep into derivatives now. So in this range, it's the value of theta equals 0 is what maximizes our cosine function. So the cosine function has a maximum value of 1 when theta is equal to 0. But then what does that mean about these two vectors, right? Because remember, what we're saying is theta is the angle between the gradient vector and the direction vector. But we're now saying that this directional derivative is going to be maximized when the angle between those two vectors is 0. So that means they would have to be pointing in the same direction. So this is when, so let me write it like this. So du, right, is maximized, right? It's the largest it can be when let me write it like this. When our gradient vector, right? So when our gradient vector and our direction vector are pointing in the exact same direction, right? So I'll say this, act in the same direction. That's a big conceptual thing, right? So act in the same direction. All right, and we're gonna come back to that concept in a bit, and we're gonna summarize these particular properties. But now we have a relatively simple condition that will guarantee this maximum rate of change, this maximum instantaneous rate of change of this surface at this point, right? It can only occur when your direction vector and your gradient vector act in the same direction. Okay, so that's the max. Well, what about the min? Well, let's think about it. It should be pretty similar because this fact hasn't changed. We're still just dealing with a constant magnitude here, right? Again, because we're at a fixed point. So then we know what would happen to maximize the cosine of theta. Then we just have to ask ourselves the comparable question: what would have to happen to minimize the cosine, right? Well, the minimum value that cosine can take on is a -1. So let's write that down. We'll just continue our bullet list here. So the cosine of theta has a minimum value of -1. And again, ask yourself what theta in this range will produce a cosine value of -1. Well, that's at the other end of the spectrum over here, right? It's when theta is equal to pi, right? The cosine of pi is -1, right? So cosine has a minimum value of -1 when theta is equal to pi. So geometrically, what does that mean? When the angle between two vectors is pi, it means they're pointing in the exact opposite direction. So our directional derivative is going to be minimized when the gradient vector and the direction vector act in the opposite direction, right? So now let's write that down. And so here we go. So the directional derivative of this function at this point is minimized when the gradient vector and the direction vector act in opposite directions, right? So they're oppositely directed. So I'll say this: opposite directions, right? And what this gives us, and remember, this expression here is an alternative formula for computing this rate of change. So the maximum will occur when this is equal to 1, which means theta has to be 0, which means delta, or del, I should say, right? Del, or gradient, and u, our unit vector, act in the same direction, which makes this equal to 1. So then the maximum rate of change will be 1 times this magnitude. And similarly, when del and u act in opposite directions, then this cosine of the angle is going to be -1, and then you'll have the minimum rate of change, right? So just by expressing our gradient, which is now by expressing our directional derivative as the dot product of the gradient and our unit vector, right? We have this alternative formula, which makes it a lot easier for us to analyze and determine what must be true to make this thing as large as possible and the same thing as small as possible. So let's go ahead and actually summarize these two important facts, and then there's another fact that I want to mention, and I'll just do that kind of separately. So the first thing that we can say is, in general now, at any point, so at x, y, the surface z equals f of xy has its maximum slope, or you can say maximum rate of change. So maximum here is referring to the largest positive slope, for obvious reasons, and you'll see why I'm emphasizing this, right? So so has its largest positive slope, or you could say rate of change, either way, right? In the direction, right, of the gradient. So it's like the gradient tells you which direction to move in, right? So move your x and y in this direction, right? So as to maximize this rate of change, right? So in the direction of the gradient. And what is that maximum slope? The maximum slope is the magnitude of the gradient, and its maximum slope is the magnitude of the gradient at whatever that point is, right? If you wanted to go ahead and put your x0, y0 there for a specific point, you could do that. It doesn't change the conclusion. This is now true as long as our gradient is well defined at any point, right? We can say that gradient gives the direction, right, in which the function will increase at the largest possible rate, and that rate at which it will increase is its magnitude, right? And then similarly, let's write something similar for the minimum, right? So at xy, the surface z equals f of xy has its minimum, and in this case it's going to be the largest negative slope, right? Because it's going to be the negative of this quantity here. So the largest negative, right, slope, but that direction is opposite the gradient, right? So in the direction opposite the gradient, right? And its minimum slope is the negative of this, right? So just looking at the gradient, so again, finding the gradient vector, right? It gives the gradient vector itself, it gives you the direction in which, like if you move x and y, your z value will increase at the largest possible rate, right? And that rate of increase will be its magnitude. Conversely, or the flip side of that is in which direction should you go if you want your function to decrease most rapidly? Well, that would be in the direction that's opposite the gradient. And then that minimum, or I should say that largest negative slope, will be the negative of the magnitude of your gradient vector. All right? Okay, so one other concept I want to talk about here, and then the question is, what if you wanted to move in a direction where there is no rate of increase or decrease? So let's say you wanted the function to be almost stationary at that particular point, right? Well, for that to happen, the directional derivative would have to be 0. So let's see this. So if if there is no increase or decrease in the surface, so in our surface f of xy, so in the surface, then it means that the rate of change is 0. So then that directional derivative would have to come out to be 0. But let's write down the alternative, the geometric way of computing the directional derivative. It's the magnitude of the gradient at that point, right? Again, times the cosine of the angle. So then let's again ask ourselves, what would have to be true for this product to come out to be 0? And as a reminder, remember, this is a constant magnitude. Magnitudes are never negative. And as long as you're dealing with vectors that have a direction and magnitude, these magnitudes are always positive. So this factor is always positive. So then it means the only way this product could be equal to 0 is then the cosine, right, would have to be equal to 0. So the cosine of theta would have to be 0. And again, theta ranges from 0 to pi. What angle in that range has a cosine of 0? That is, drum roll, pi over 2. So what this means is, if the angle between the gradient vector and your direction vector is pi over 2, which means they're orthogonal, then the rate of change of your surface will be 0, right? So let's write that down. Let's kind of finish it. So if there is no increase or decrease in your surface at that point, right? So like your z value is neither going up nor down, what that means is your direction vector and your gradient vector would have to be orthogonal. So I'll just kind of write that down here, which means the gradient at that point, oh, I forgot my y. Let's fix that. So y. So my gradient at that point and my direction vector, so which means these two vectors must be orthogonal. So they must be at 90 degrees, right? So the way you would sort of interpret this, and let me now do a little sketch. So let's say that here's our point, our x0, y0, and let's say we can find the gradient at this point. So I'm going to sketch the gradient. So if let's say my gradient goes this way, okay, so that's my gradient vector at that particular point. If you now have to make a decision in what direction you should be, so if my u goes this way, right? So if my u vector is parallel, and acting in the same direction as my gradient, then what it means is that so this would lead to my surface, so f of xy would increase, so I'll say increases at the largest possible rate, right? Largest possible rate. That's when u and del point in the same direction. If your u and del point in the opposite direction, so if that's your u, then what this means is you could say f of xy. We know the rate is going to be negative, right? So we can say that f of xy would decrease. So decreases at the largest possible rate. So in other words, if you change your x and y headed in the red direction, that would cause your z value to decrease at the largest possible rate, because it will be the negative of that magnitude. If you decide to move in a direction that is orthogonal, right, to my del vector. So notice del is fixed. I'm basically writing down all the different things that we can say now about u. If u is either that way or that way, where there's a 90-degree angle, or pi over 2, between my u vector and my del vector, this means that there will be or the rate of change of my surface will be 0. So this implies that the rate of change of fxy is 0, right? If there is any other angle, so going in any other direction, not red, blue, nor green, then you'll have some other rate of change. It's not going to be as small as the red. It's not going to be as large as the rate that's obtained by going in the blue direction. It's going to be somewhere in between. But essentially, what we've highlighted here with the red and the blue are the extreme cases, right? So again, think of it this way. You're at a specific point and you have to make a decision. in what direction do I change x and y? If I want to get my function to increase as quickly as possible, then I'll move in the direction given by the blue vector. If I want to make the function decrease as quickly as possible, then I move in the red direction. And if I want to have no change in my function value or my z value, then I'll move in a direction there by the green. So I kind of have two choices here. Again, it's just because of this orthogonal property that either this direction or this direction, the angle between the u and del is pi over 2. All right, so let's just do a quick example illustrating this, and then we'll wrap up this look at, again, a very important property of the gradient. So let's pick again, not a super complicated surface, but let's say my surface is x squared e to the y. And what I'll do is I'll just kind of go through highlighting these three properties. Now let's pick a point. Let's say we're at the point -2, 0, so something like that, right? And we're going to go through, we're going to find in what direction, so starting at this point, in what direction should I move, right, in order to get the greatest increase in our function, rate of the greatest rate of increase of our function, right? And then in what direction should we move to get the largest decrease in our function, and in what directions could we move to get no change at all? So let's answer all three. And they all start with the gradient. So let's compute the gradient of this. And first I'll write it down in terms of x and y, and then we will evaluate it. So the gradient is that vector where we fill out the components using the respective first partial derivatives. So the first component is the first partial derivative with respect to x, which in this case is 2x e to the y. And then with respect to y, it's the same, right? Because you bring down your x squared, that's your constant multiple, and then the derivative of e to the y with respect to y is e to the y. So now let's evaluate the gradient at this specific point. So the point here is -2, 0, and if we plug in these, we will get -4, right? Yeah, so this will be a -4, and then this will be a +4, right? So what we can say is this: if we wanted the maximum, so the direction and maximum rate of increase, then we would move in this direction. And let's say we wanted to define what the u should be. Now the u has to be a unit vector, so we're going to go ahead and normalize it. So the direction would be u equals, now the magnitude of this is the square root of 32. So I'm not even going to really simplify it, but I'll have 1 over root 32 and then -4, 4. So if my u is equal to this vector, then my surface will observe the largest possible rate of increase. And what is that maximum rate? So this is the direction, and then the maximum rate will be the magnitude of the gradient, which is the -32. So I'll say with a maximum rate of root 32. If I wanted the direction and maximum rate of decrease, and that's the way I'm saying it, so like going down at the fastest rate. So if I wanted the direction and the maximum rate of decrease, then I would just have to go in the direction that's opposite to this. So I would use the negative of u. And again, this would be now 4 over root 32, negative 4 over root 32. And then with that maximum rate of decrease, which would be negative root 32. So with a max rate of decrease being negative root 32. So maybe for emphasis, I should put max rate of increase there. There we go, right? So again, if we're starting at this point, and if we move, if this is our unit vector of direction vector, then we would observe the largest possible rate of increase in our z value, and that will be root 32. If we go in a direction that's the opposite of that, we will observe the maximum rate of decrease being negative root 32. What if we wanted the direction of no change, right? So what if we wanted no change? So direction of no change. Well, meaning the rate's going to be 0, we would have to move in a direction that is orthogonal to this, right? It has to be at 90 degrees to this. So remember, one of the ways, if you have a single vector and you're trying to find a vector that is orthogonal to this one, you can switch the components and then change one of the signs. So switch let's say I switch the 4 and the negative 4, and then I make the negative 4 positive, right? So then this would be one direction that would work. But again, if we wanted to make it a unit vector, then we would normalize this, right? And so basically we could have done that switch and change on one of these vectors. But I just wanted to remind you that this one is not unit, right? And then if we normalize this, we'll end up getting 4 over root 32, not 33, so 32 comma 4 over root 32. And that vector now will produce a directional derivative, right? A rate of change which would be equal to 0, right? So I'll just say rate of change is 0, right? And that is, again, a very key property of the gradient. It tells you in what direction you would have to move if you want to go up as quickly as possible, down as quickly as possible, and also if you want to move in a direction where essentially your elevation doesn't change, right? And there we go. So that's our first important property of the gradient, and the sequel is coming up next. See you then.